All right, so now let's talk about reactions that we can do starting with alcohols. What's going on here? There it is. All right. Um, so the first one is the first one that we're going to study is how to convert alcohols into alkyl halides, and this is very similar to how we converted alkyl halides into alcohols. The key thing here is that we're going to do substitution, but this right here is a pretty bad leaving group. So the first step in a lot of these substitution reactions with alcohols is you first have to create a better leaving group. All right, so in terms of, this is sort of the simplest one, which is the acid catalyzed. What you're going to do is you're going to use some strong acid. What that will do is that alcohol oxygen is going to reach over and grab that acidic proton. So you have this proton transfer. What that does is create this right here, and this is a good leaving group. Okay, so by protonating an alcohol, we can create a good leaving group. And so in the case of a tertiary alcohol, that will actually just fall off, creating a carbocation, right? So we'll lose water. Water will be our leaving group. Now we have this carbocation, and we can have the bromide ion playing the role of a nucleophile and attack that electrophilic carbocation. And that will give us our alkyl halide there, our tertiary alkyl halide. For primary and secondary alcohols, it's pretty much the same process, except for instead of being an SN1 reaction, it'll be SN2. Again, first step though is you have to protonate that alcohol in order to make it a better leaving group. But we know that this isn't just going to fall off because it wouldn't create a very stable carbocation. So instead you have an SN2 reaction where that bromide ion attacks that carbonyl carbon at the same time as that leaving group gets kicked off. Okay, so by using HBr in the presence of an alcohol, we can create an alkyl halide. You can do the same thing with HCl, but it turns out to be incredibly slow. So one way around that is to use zinc chloride as an additional catalyst. And what zinc chloride does is very similar to the role of protonating that alcohol group, is it makes the alcohol group a better leaving group. In this case, the zinc chloride actually forms a bond with the alcohol group. And now this is a good leaving group, so that chloride ion can attack and kick off that good leaving group. Okay, so HBr works by itself. HCl, you want this zinc chloride in to help catalyze that reaction. But again, the whole sort of shtick is that you're making your alcohol group into a good leaving group before you have that nucleophilic halide ion coming in substituting. Another way to convert the alcohol into a good leaving group is to use what's called a Tosyl group, all right? And this is abbreviated as TSCl, so Tosyl Chloride. I mean, if you're curious, is this big ugly thing here. Bottom line is, in the presence of pyridine, this is just a solvent that we use here. You can substitute, I don't know, substitute's not a good word. You can attach this Tosyl group to the oxygen, creating this really good leaving group here. And this can undergo substitution with a halide ion, or really just any nucleophile would work here. So a halide ion, we know those are good nucleophiles and poor bases, but really any nucleophile could be used here. Sorry. Any nucleophile can be used. Because basically the whole shtick of the Tosyl group is that it's just a great leaving group. So by adding Tosyl chloride to an alcohol, you've converted your really bad hydroxyl leaving group into a really good Tosyl leaving group. Okay, and then, as is always the case with the SN2 reactions, you have to worry about stereoselectivity because you have that inversion that occurs, right? So if I had Tosyl chloride, right, this first step is creating a really good leaving group. and then I added that bromide ion, I would have an inversion in my stereochemistry. Other ways to generate alkyl halides from alcohols using SOCl2 in pyridine or phosphorus bromide, tribromide. The benefit of these is that they don't react with other functional groups, right? So HBr or HCl, they'll react with alkenes and alkynes. These ones won't, okay? So they're a little bit more designer type, but I bet they're more expensive. But again, they're more specific to reacting just with an alcohol functional group, okay? So they're a good way to convert alcohols into alkyl halides as well. For elimination reactions, we can do an elimination reaction with an alcohol as well by using concentrated sulfuric acid and heat. And remember, this is kind of interesting because we know that we can use dilute sulfuric acid in order to do a hydration reaction of an alkene. We use dilute sulfuric acid because that means there's more water molecules floating around in solution that will do the addition. Turns out that if we use concentrated sulfuric acid and heat, we get the elimination product. And notice that heat is good because this side over here, this is higher entropy because 2 moles of products are formed, whereas this side over here is lower entropy because there's only 1 mole of product that's formed or reactant. All right, and so the more molecules, the more small molecules are formed, the higher the entropy. And so that's why when we use heat, we can help favor that higher entropy product. The mechanism here, same deal as before, right? What do we got to do? We got to convert our bad hydroxyl leaving group into a good leaving group. So that alcohol is, oxygen is going to reach over and grab that really acidic proton from the sulfuric acid, creating a really good leaving group here. So then the second step is that loss of leaving group. Then we have this carbocation. That carbocation will then undergo a proton transfer where the water reaches out and grabs that proton, and then the electrons that were in this carbon-hydrogen bond now form your double bond. Okay, so again, just like we saw with the HBr and the HCl, it's all about making that alcohol group into a better leaving group. Because of the mechanism, because you're going through those carbocation intermediates, you will always produce the, right, this is the Zaitsev product, or that more highly substituted alkene will be your major product. If you wanted to produce this as your major product, the less highly substituted alkene, we can only do that with E2 type reactions using a bulky base. But notice that you can't do these kind of dehydration reactions with a bulky base because you have to have the acidic conditions, right? An alcohol group will not be a good leaving group in basic conditions. So if you really wanted to get the Hoffman product, what you would do is first convert your alcohol to a good leaving group, not by protonating it, but by using the Tosyl chloride, right? So again, all Tosyl chloride's doing is it's creating a really, really good leaving group. So now, and again, you can just imagine that here, all you see is great leaving group. Well, we can get the Hoffman type product by using, by using a big bulky base. In this case, it didn't really matter. They just used the alkoxide. In this case, it's an alkoxide ion. Just a really good base will create that elimination product. If we wanted to go back to this reaction here, when we use our Tosyl chloride in pyridine. Remember that that PY represents pyridine, just a solvent. Now we create, oops. Now if we use something like, whoops, tert butoxide, that would give us the Hoffman type, a big bulky base, right, would give us that Hoffman type product as our major product. Okay. All right. So now just to review, we've got a bunch of different ways, right? So we've got these are ways of generating alkyl halides. Again, the benefit of using these more designer substrates down here is no side reactions with other functional groups, right? So if there was an alkene or an alkyne functional group, you could use these two reagents in order to create an alkyl halide that won't react with those two. These are kind of your rough and tumble up here, just using HBr and HCl. Those will definitely do the job as long as you only have that alcohol functional group. Remember, they will go through a carbocation intermediate, so you might have to watch out for rearrangements, okay? All right, so now in terms of our little cheat sheet, in terms of mechanism, you should know it for the acid catalyzed ones, right? So in the presence of HBr, this is either SN1 or SN2. Okay, with the Tosyl chloride, these are going to also be SN1 or SN2 or E1 or E2, all reaction mechanisms that you should know, right? So it would really depend on the alcohol that you started with, because the bottom line is when you add that Tosyl chloride, all you do is create a really good leaving group. So this can undergo substitution, or if you had just a really strong base, especially if it was bulky, you would actually favor the elimination product. Mechanism for these guys, you don't have to worry about. I think actually the book gives you that. I wouldn't worry about it. Okay. And then in terms of the acid catalyzed dehydration, you should know the mechanism for that as well. In terms of regioselectivity, for substitution type reactions, you don't have to worry about it. But in terms of the elimination reactions, you should know the elimination, how that will favor the Zaitsev product in the case of a non-bulky base, or the Hoffman product in the case of a bulky base. Likewise, when you have the dehydration, you're going to get that Zaitsev product, right? There's no way, because it's going through this carbocation intermediate, there's no way of tuning it so that you get the Hoffman product only. If you wanted that Hoffman product, you would want to go through and use that Tosyl chloride. And then in terms of stereoselectivity, so certainly if it's an SN2 reaction, you want to make sure that you know the stereoselectivity of that. Also, E2 reactions, remember they have by far the biggest pain in the butt at stereoselectivity when there's only that one beta hydrogen, so keep that in mind. Luckily, you don't have to worry about it with those because they're just simple substitution reactions. And then in terms of stereoselectivity, for the concentrated sodium chloride, yes, you want what do we call that? Favored trans product. For the most part, you could say that really bulky groups on opposite sides. Right, so that's always going to be the more favorable alkene that's formed. It's when the bulky groups are on opposite sides of the double bond.